All right, good morning, class. We are going to finish lecture 1 today. We just have a couple more slides to go, nothing too complicated. And then we're gonna move on to lecture number 2. Just take a look at the schedule here. There will be nothing due this week, no quiz, no lab, no assignments, okay? And then your first quiz will be next Thursday, All right, I'll tell you more about it later on. Okay, you by the end of this week, you would have learned everything that is on quiz number 1. Okay, it's just all of lecture 1 and all of lecture 2. So we learned about setting up experiments that involves humans, right? We have to have the control group. We have to have the treated group, the group that is receiving the experimental drug, for example. And then we also need to include a placebo to eliminate bias and psychological effects. Now, there are other things that needs to be considered when we do an experiment, and we want it to be good science, okay? And there are a couple of factors we need to consider when it comes to that. We want the sample size to be as big as possible, right? The population over here is really, really big. And we want to randomly select people from the population to have a representative sample group to run our experiment on, okay? The larger the group, the more reliable the result is going to be. If you think about testing the vaccine, right, you don't want to just test it on 100 people, right? That's not very conclusive data. You want to test it on thousands and thousands of people before using it in the world population, right, which is like, close to 8 billion people, right? So you want to have a good representative sample, and you want to choose the people randomly, right? And it depends on the purpose of the experiment, right? Sometimes you want to test it within a specific age group, right? Then you want to be selecting people from that group, right? Like rather than having a wide range group. But what I mean is you don't want to put like all the young people in one group and all the older people in another group, right? The result will not be accurate. Other things you want to consider would be, having a mix of ethnicity, unless the test specifically want to see how the drug behaves differently in, different ethnic groups, right? And that would be a different story. But otherwise, you want to have a good mix, right? Good mix of people with different genders, people with different occupation, and so on and so forth. That way, right, we are not skewing the results one way or the other, and it's part of our effort to standardize the experiment. There are other things we have to consider. What kind of testing should we be doing, right? Do we include a placebo group? Sometimes placebo might not be necessary, right? Even when it comes to human. Like I said last time, if you're doing a vaccine test to see if it's working, there's no psychological effect to eliminate, right? So the placebo group and the control group happens to be the same thing in this case. Sometimes deciding what the placebo is also not an easy task. And who should participate in the experiment? So you might remember, I think it was in 2008 that there was an outbreak of Ebola, right? And they didn't have a vaccine at the time. There was a vaccine that was in development in Canada that has shown some efficacy in animal testing. But because there was no outbreak at that time, they stopped after the animal testing, right? So it's promising on animal testing, and now there was an outbreak, so they wanted to use that to test it on humans, basically to continue to research, right? So who should participate in that study? That was an ethical concern. Should we allow the healthcare worker to be in the group? Right? Because they are the one who's going to be taking care of the patient, right? Should we maybe include the elderly because they are the vulnerable population, right? So who gets to go first, right, on this potentially life-saving vaccine? Sometimes it's not so easy to decide. and when to mass produce. Pharmaceutical companies don't want to create a lot of a new drug before they know is going to work or not, right? Like, what if you make this whole invest all this money to make all these vaccines and it turns out to be ineffective? Then you waste money and you waste resources, right? So normally speaking, they don't do that. They wait until the trial is done and then they mass produce. But the main drawback on that is if there is like an outbreak going on, in this case, the Ebola, right? It might be too late to mass produce until when you wait until the testing is all done, right? A lot of people could have died along the way. So in the case of COVID, what happened was the government stepped in and they were like, you know what, you guys go do the testing, and at the same time that you're testing, you can go ahead and mass produce. And at the end of the testing, if the results are promising, if it's working, then we would already have all the shots ready to ship out, right? And if it doesn't work, that's okay. The government will absorb the cost, right? So that way they're not going to be losing money. And that's why it was able to roll out so quickly for the COVID vaccine, because things are going alongside, right, parallel to each other, instead of one after the other. But these are ethical questions that needs to be considered. Now, a lot of times in research, people would identify trends. People would identify correlation between two variables. So here we have, for example, like stress level and versus how often you get a cold. You can see as a person gets more stressed out, they're more likely to catch a cold. So someone might look at this data and then they would say, okay, stressing out is going to cause you to more likely to catch a cold. But that might not be the case, right? It's not necessarily a direct relationship. Right? There could be some other underlying factors that is causing the person to have cold. For example, if you have other illnesses, if you have poor diet, little exercise, not enough sleep, all these factors is going to cause you to be stressed out a little bit and probably cause you to have a higher chance of having a cold as well. So just because you see a relationship, a correlation between two factors, stress and high frequency of cold in this case, does not necessarily mean one causes the other. So we have to be careful. There is an interesting website you can click on to look at if you want. It shows you trends that are very similar to each other, but they have absolutely nothing to do with one another. For example, the blue graph here shows the number of people who died by becoming tangled in their bed sheets. That's apparently a thing that actually happens. And it almost perfectly coincide with the number, the amount of cheese that is being consumed per capita, right? So if you look at these two graphs, you're like, okay, it looks like the more cheese you eat, the more likely you will die in your bed because you're going to strangle yourself with the bed sheet, right? But obviously, the two things are not related to each other. Okay, so the key thing to take away is correlation does not imply causality. Just because two things looks like they're related does not mean one causes the other. And when we look on the internet, there are a lot of false information on the internet, especially nowadays with AI and all that stuff. There is this prevalence of false information that is spreading, and it's not slowing down any time. And there's a lot of clickbait, right? Like you read the title and people don't go through the trouble of reading the article. They just look at the title and then they assume it is going to be true, right? Especially when it says a study found that, or scientists find that. As people see these words and they automatically assume it is credible, right? And even though it's a scientific study, at the end, it might not be good science, right? Like you have to look at a lot of things. You have to look at who's doing the study, who's funding the study, right? Like did the study have the proper control? How many people were involved in the study? There are a lot of factors that we need to consider when we try to decide if the study is credible or not. So I did a quick search on Google. I'm sure a lot of you drink coffee. I used to drink it as well, not anymore, but I switched to tea for like, I guess healthier. I don't know if it's healthier, but like it feels healthier for me. Okay. But coffee, right? Like you drink coffee for different reasons. But some people say coffee is good, some people say coffee is bad. And then I just did a quick search, right? On Google, and I found like opposing studies, right? Drinking more coffee might reverse liver damage from booze. So that's like a good reason to drink coffee. Party all weekend, and then you cleanse yourself with coffee during the weekday or something. But here it says coffee consumption in either parent may raise miscarriage risk. Okay, so these are like opposite views, right? And then here you see something say coffee consumption may help prevent colon cancer. So there are like all these studies. Same thing with drinking like red wine, right? Like some studies say it's good, some studies say it's bad. The point is a lot of these is just the key word to see is may, right? May, right? That and over here, may. It's just a correlation, people, right? It's not necessarily a definitive cause and effect relationship that we're observing, right? So when we see these things in the media, when we see these things, hear these things in the news, right? We have to put on our filter. We have to think about what is really done behind the scene. We can look up these studies and then use our understanding of scientific method to see if they are actually good science or not. So for me personally, I don't really pay attention to these things. I just do as I please. YOLO, right? You only live once. You eat what you want, you consume what you want, and then you can bear the consequences later. That's my view. So whenever someone tells me, send me a link and say, oh, you should stop eating red meat because it increases your risk of whatever, I just like leave me be. I will eat my red meat if I choose to. Now, how do you know if something is like, good science or bad science, right? How do you know it's a good source or not? Well, typically speaking, primary sources are more reliable, okay? Typically speaking, they have firsthand information that is provided by the person who's doing the study, okay? So you have the researchers who conducting the experiment, they submit a paper about the results to usually some kind of professional journal, okay? And these journals, they are peer reviewed, which means in order for them to publish the result, some other experts in the field has to scrutinize it. Okay, they have to look at the experiment. They have the expertise to critique the work and then make sure it's of good quality before I publish it. So generally speaking, they are more reliable. Okay, like a blog online, that's not necessarily credible, right? Because any one can write something on a blog. There is no peer review mechanism in place, and it might not be accurate, right? So primary sources are generally more accurate, but they are difficult to understand, okay, for the general public. Okay, unless you're like in the scientific field studying that very specific thing, it's very hard to read a peer review article. Okay, we might not even have the expertise to understand everything in the article, which is why most of us, including myself, we look at secondary sources, right? So these are people who've read the article, they probably have a reasonable understanding of it, and then they write a summary about it. So these could be news article, these could be like in a textbook, right? Those are secondary information. It could be like something that you read in a magazine, right? So all these are considered as secondary sources, right? Depending on where the secondary source comes from, like if you read it from like the New York Times, for example, right, or you read it from Toronto Star, it's reasonably accurate, you would assume, right? But if the secondary source is just some kind of, again, internet blog, or if you read it from Reddit or something like that, then it's less credible. Okay, so when you do your research in your other courses, right? I'm sure you have to do researches, right? Research projects for maybe your genetic course, maybe in your English course. You have to evaluate the type of sources that you're using. And that's it. That's it for lecture one. Congratulations, you've done it. Okay, you've finished 10% of the course. That's one lecture out of 10. Do we have any question before I move on to lecture number 2? And I just want to thank you guys, right? I look at the attendance. You guys have very good attendance, all right? Like this is the third day. I've been doing online for, since even before the pandemic started, and attendance start to drop usually starting as early as the second week of class. But I see that we have 27 students here. The class is like 30 people. So I just want to thank you guys for your commitment and being here and doing the learning. Okay, having said that, let's move on to lecture 2. All right, so lecture 2 is finally gonna be more biology related. Okay, so far the stuff we're learning is just like general science stuff, right? And now we're gonna shift towards the bio stuff. But before that, I have to teach you a little bit about chemistry. I know you have your chemistry class with Professor Chung, but I'm gonna teach you some chemistry just to make sure that you have enough to understand what you need to know about macromolecules. And thank you for the kind comments in the chat box, guys. All right, so basic chemistry. Matter. Matter is anything that takes up space and has mass. Okay, so there is volume to it. It's heavy, it weighs something, right? I mean, not necessarily heavy, but like you can put a weight to it. Okay, it has a mass associated with it. So everything that is surrounding you right now in your room is made up of matter. The table is made up of matter, computer, the phone, all these are matter, okay? It can exist in solid, liquid, or gas. You probably knew that already. And of course, they could cycle through the different states depending on how much energy you put in the substance, right? So typically, the more heat you give it, the more energy you give it, it will become more energetic, and then it will go from solid to liquid and then to gas. All the matter that we know is composed of what we call elements. Elements. Okay? So these are substances that we cannot break down further. Right? It's the simplest substance that exists in the universe. You cannot physically break it down any further. So what makes up the element, right? Okay. The smallest unit of an element is an atom. And I'm sure you learned about atoms already in chemistry class, but here is a typical atom. You would have a nucleus in the center, and there are two subatomic particles. These are things that builds up an atom. Yeah, so we have the protons, which are positively charged, P for positive and P for proton. Some are electrons that goes around the nucleus, just like planets going around the sun. These are negatively charged. And we have neutrons, which have no charge. Okay, so protons and neutrons, they come together to make the nucleus in the middle, and then you have the electrons that are flying around the nucleus in orbits. So that is your typical atom. All the elements that we have discovered in the universe so far is listed on the periodic table. If you can find it on the periodic table, then it is an element. I cannot find water, for example, on the periodic table. So water is not an element, okay? So some of these things you know, right? Hydrogen, right? Carbon, sulfur. Right? You will come to remember some of these as you progress through your chemistry course. So many elements here, right? Like 118, and sometimes they can even have more if they artificially create some in the lab. That sometimes happens. But in terms of humans, over 96% of the human body is composed of just 5 elements, even though there are hundreds of them, okay? 5 of them makes up a majority of the body. These include things like carbon. Where do we find carbon in everyday life? Anyone want to tell me? Where do we find carbon? Okay, yeah, sure, carbon dioxide, but I mean like the act, just like like carbon by itself.
Sorry, carbon by itself, we can find it in the atmosphere or in underground.
Underground. Okay, so I all of you are kind of saying, there is carbon dioxide in the air, right? So dioxide means it's actually with oxygen. So yes, there is carbon, but not by itself, with something else in the air. Anything else? It's probably on your table right now, or like it might be on your fingers. Some of you might have it on the finger. I don't know. I'm just guessing. No?
Are you talking about carbon fiber?
No, I'm talking about carbon by itself. Yeah, carbon. Nails, okay. Okay, diamond. I'm talking about diamond. Okay, diamond. You guys,
Diamond.
some of you might have a diamond, right? I don't know. Hopefully, your spouse got you one. I don't wear mine anymore because it's dirty. The COVID thing got me like all worried about things getting into it. Anyway, actually a fun story. This is not related to what we're talking about, but diamond is carbon. And my wedding ring has a couple of diamonds on it, okay? And like just small, tiny one, all right? So one day, I was just sweeping the floor, and then my kids, they do arts and craft, and then they have those little sparkly things, that you can put on your calculator or on your phone, those sticker things, right? So one day I was cleaning the house, and then I saw saw a sparkle on the corner of the floor. So I was like, oh, these kids like make the house so messy, and then I threw it away, right? And a couple weeks later, I noticed I was missing a diamond on my on my ring, and then I told my wife, I was like, oh no, I think I actually threw it away, thinking that it was like one of my kids' sparkle thing. Anyways, I so like I'm missing a diamond. Whatever, that's just a story to tell you. But carbon, yes, carbon is a diamond is carbon. Graphite, okay, your pencil is also made of carbon, okay? So the charcoal is made of carbon, right? And our body has a lot of carbons in it. In this picture, you can see like 18% of the body is made of carbon. Next one, nitrogen. Nitrogen is in the atmosphere, 70% of the air that we breathe is nitrogen. Okay, we don't use it though. We breathe it in and we breathe it out. Okay, we cannot use the nitrogen as is in the air. You might have some nitrogen in your tires as well. Right? Oxygen, 21% of the air that we breathe is oxygen. Okay, hydrogen. People used to have use hydrogen to pump up balloons, but they are flammable, so they switch it to helium. And phosphorus. Okay, does anybody know where we find phosphorus? It's probably in your kitchen somewhere, maybe.
In the shrimp.
In the what? I'm sorry?
Shrimp.
Shrimp? Oh, yeah. Okay.
In food?
Not, well, yeah, in some of the food, but not by itself though, right? I guess what I'm getting at is matches, okay? Matches, okay? So phosphorus is what causes the match to light up, okay? It's in the match strip, right? So anyway, these are the key elements that is found in the body, all right? That makes up over 96% of what we are, right? So when we learn the macromolecules in the class, we are going to look at, proteins, what are proteins made up of, right? We're going to look at what, DNA is made up of. So we will keep in mind what these key elements are as we learn learn the macromolecules. So what about the rest of the body? What about the remaining 4%? Well, we have these things called trace elements. Okay, trace elements are elements that are required in small quantity. You don't need a lot of them. Okay, and in fact, if you have too much of these trace element, you could be poisoned by them. Okay, not having enough is also a problem. Okay, so you just have to have the right amount, small amount of them in order for the body to function. Deficiency, meaning not having enough or too much, is going to be bad. Okay, so here are some examples. Okay, we have zinc, which is needed for your immune system. Many of you probably know calcium is important for bone growth, right? Strength of your bones, but you also need it for muscle contraction. Every time you move any part of your body, you actually need to have some calcium to do it. Iodine is needed to make a hormone from your thyroid gland. Okay, do you guys know where your thyroid is? I usually ask people to show me in class, right? Like show me where your thyroid is. Okay.
Neck.
Yeah, very good. Okay, Justine, it's right here. Okay, you have a butterfly-looking gland here called the thyroid gland, and it uses iodine to make hormones for you, right? To help you regulate your metabolism. So we do need a little bit of iodine and magnesium, something else that we need for muscle contraction. Okay, maybe some other example that you guys know. Okay, what is it that is in your blood that helps you carry oxygen, huh?
Red blood cells.
Right, but what element is important in those cells?
Iron, the
Iron.
hemoglobin.
That's right, iron. The iron is in the hemoglobin, and that helps you carry oxygen, right? So if you have iron deficiency, then you're gonna have anemia, right? Okay, so again, just having the right amount. If you have too much iron, right, that could also lead to toxicity in your blood. Okay, maybe just one other example of trace elements that you can think of. What else? What else do we need in the body, huh? Potassium, that's right. If you drink your sport drinks after exercising, look at the label, they have potassium in it. And we need potassium for various things, okay? Like your neurons needs to have the right potassium level to communicate with each other. Now, I do want to clarify something, okay? When we say we need calcium, okay, it's not talking about the elemental calcium. Okay, it's like what calcium looks like. Calcium by itself, what it looks like, it's a solid, and that is very reactive. If you drop a chunk of calcium into water, it will actually react violently and produce a lot of sparks and smokes. Okay, you can actually search it up on YouTube. Same thing, when we say we need sodium, we don't mean the elemental sodium in its solid form. Okay, what we do mean is we need these things in their ion form. Okay, so more on that later. So for zinc, we're gonna need it in like zinc 2 plus. For calcium, we're gonna need it in calcium 2 plus. Did you guys learn this in chemistry yet with the ions? Just wondering, or not there yet?
I don't think we're there yet.
No? Okay. So I'll explain what that means later. But what I want you to understand is it is not the element that we are talking about. Okay, not like a when we say we need iron in the body, I'm not talking about like a piece of nail, right? That we need to ingest, right? It is the ion form that we need. More on that later. Here are two examples of what happens when you don't have enough trace elements. Okay? So iodine deficiency can lead to goiter. Right? The thyroid needs the iodine to make the hormone. I told you. When you don't have enough iodine, the thyroid tries to get bigger, right? Hoping that by increasing in size, it could pump out more hormone to compensate. Okay, so that's called goiter. We usually don't have to worry about iodine deficiency in North America. Why is that? Where do we get our iodine from?
From salt.
That's right. Our salt are iodinized. Okay, the manufacturer, I guess, they add iodine to the salt to prevent this kind of thing. Okay, natural sources of iodine would be like shellfish, right? Seaweed, those kind of things are particularly rich in iodine. But like I said, we don't have to worry about it. Calcium deficiency can lead to osteoporosis. The bones becomes very porous, and then you can break them when you fall. All right, moving on, we have something called isotope. All right, if you look at the atoms of an element, let's pick carbon, for example. Not all carbon atoms are the same, okay? It turns out some carbon atoms are heavier than others, okay? The carbon atoms, they sometimes have different number of neutrons, okay? Different number of neutrons. You cannot change the number of protons. If you change the number of protons, it becomes another element altogether, okay? So carbon has 6 protons and 6 neutrons. This is what we call carbon 12. Okay, 6 plus 6 gives you 12. Right? It's going to be 12 unit heavy, and we call it carbon 12. And then there's something called like carbon 14, which is 6 protons, but it has 8 neutrons. 6 plus 8 gives you 14. Don't worry about the math. I'm not going to ask you about it, but I just want you to know that sometimes the atoms of the same element, they can be heavier, right, than the general one because they have extra neutrons. So we call these things isotopes. Okay? The heavier they are, sometimes the more unstable they become. And then when they're unstable, they break apart on their own. Right? And sometimes when they break apart, they give off radiation. So we call those radioactive isotopes. Now we use radioactive isotopes for various reasons. If you find a fossil and you want to know how old it is, you can check to see how much carbon-14 is left in the body. So all of us who are like alive, we have a set level of carbon-14. Okay, and we maintain that level because we constantly bring in new carbons from the environment, right? We breathe them in, we eat them, and so on and so forth. There's carbon in the food, for example. So we have a constant level of carbon-14. All living things has a constant level of carbon-14. But as soon as they die, right, as soon as we die, we no longer exchange carbon with the environment. So whatever carbon-14 we had at the moment we die will continue to break down, okay, over years and years and years. Right? So when you have a fossil, you see how much carbon-14 is left, you can work your way back to see when the thing died. That's basically how it works. Iodine-131 is another radioactive isotope. For people who have thyroid cancer, they could the radiologist can inject iodine-131 into the body. It will go to the thyroid, and as the isotope breaks down, it gives off radiation, and the radiation will kill the cancer cell, ideally speaking. If you have a smoke detector at home, there is a little bit of americium-241 in it. It's radioactive isotope, and that is basically what's kind of like powering the smoke detector. When the smoke goes into it, it interrupts the circuit, interrupt the radiation a little bit, and that's what sets it off. Okay, so these are just some examples of where we use isotopes in real life. But isotopes are basically atoms of the same element that has different number of neutrons. So here is another variation. Okay, an atom can gain or lose electrons. Okay? And why they do that, I will let your chemistry teacher explain to you, but I'll give you an example. Let's say we have sodium here, sodium, Na. Sodium likes to give off an electron. And when they lose an electron, remember, electrons are negatively charged. So when they lose an electron, they become positively charged, like that. So when you look at your sport drinks and they say they have sodium in it, They are not talking about the elemental sodium. They are talking about the ion form. The ion form, ion, means it has either gain or lose electrons. Same thing. We need chloride in our system. Okay. So what is chloride? Chloride is basically chlorine plus an electron, and because it gains an electron, it becomes negative charge. Okay, so these are called ions because they have either lost an electron, is given off, or they have gained an electrons. Right? So all these ions that we need in the body, we generally call them electrolytes. Electrolytes. Okay, and electrolytes are very important. Right? If you sweat excessively, you become dehydrated. You can't just drink pure water. I mean that like if you don't have other choices and pure water is all you have, sure, drink it, right? But it's actually better to drink electrolyte, okay, to replenish all these lost ion. Okay, that's why sometimes people who like they have like food poisoning, diarrhea, or something, right? Especially in kids, right? You have to give them these. It's called Pedialytes. Okay, it's basically electrolytes that you give them, because when you have diarrhea, you're not just losing water, you're losing electrolyte as well. And if you only replenish with water, you are actually diluting the remaining electrolytes in your body, and that could make the situation worse. Right? So you have to replenish the electrolytes. All right. So I've been talking a lot so far. Do you guys okay? Any questions you have for me? All right. So let's take a closer look. Right? We have the element here, sodium element. That's what sodium looks like. It's a chunk of solid. It's actually very soft. You can cut it with like a butter knife. And you can see the person is wearing glove because it's really reactive with moisture. Okay, even moisture from your skin is gonna set it off, right? So you have to handle it carefully. You have to store it, under oil, for example. And what makes up sodium? Well, we have these sodium atoms here represented by the blue balls. And then we have chlorine here. Chlorine is a gas and it's poisonous. Okay, chlorine gas was used in the Second World War as a mustard gas to kill people, basically. If you breathe in chlorine, it is going to destroy your mucous membranes, right, your lungs, and it's a horrible way to die. And what is chlorine made up of? Chlorine atoms. Okay, so little triangles here. But when you combine sodium and chlorine, you get sodium chloride. Okay, sodium chloride is table salt. Okay, even though sodium and chlorine on their own are very dangerous, one is explosive, the other is poisonous, but when they come together to form the compound, the property is completely different. Okay, and table salt is very stable. In fact, we can consume it, and that's what a compound is. Right. So when you take sodium chloride, when you eat it, right, in the body, they become the ion. They become the sodium plus and the chlorine minus. All right. So that's what we need in our bloodstream, in our body, in our cells, right? Not the elemental form that I kept on talking about. You understand that? Same thing, right? When we say there's chlorine in the pool, we don't mean chlorine gas. Okay, we mean the elemental form. Sorry, the ionic form. So the smallest unit of a compound is a molecule. Okay, we make compounds by taking elements and putting them together. Remember the picture of the periodic table, right? There are like hundreds of different elements. You can take them together and form the compound. Earlier, someone was saying carbon dioxide, right? Carbon dioxide, CO2. So it's 1 part carbon and 2 part oxygen. Okay, you have 1 carbon atom in it and 2 oxygen in it, and it forms a compound. All right, and the smallest unit of a compound is a molecule. Molecule. So there are 2 kinds of glue that holds the atoms together in a molecule. Okay, we can have what's called an ionic bond. That's what this is showing. In an ionic bond, there is a transfer of electron. Okay, sometimes more than one. So the sodium wants to give away an electron, chlorine wants to take one up, and then they would partner up and form a strong bond. And you can see there's the Na plus that I told you about earlier, and then there is the chlorine minus, right? And this holds it together. They become very stable. So that is the ionic, okay? Ionic bond. And then over here we have a covalent bond. Right? In covalent bond, instead of transfer of electron, we have a sharing of electron. And sometimes it's more than one, right? And that's what's holding the oxygen and the hydrogen together. You will learn more about this in your chemistry class. For now, just understand there are two kinds of glue, right? The glue is the bond. There are two kinds of glue that holds atoms together. Either is an ionic bond, which involve transferring electrons from one atom to another, or it could be a covalent bond, which means they are sharing the electrons. Okay, so ionic bond generally is stronger compared to covalent bond. All right, so these are harder to break apart compared to covalent bonds. Okay, please let me know if you have questions. Just interrupt me anytime. So now we know what molecules are, right? They are multiple atoms coming together. And if it contains a carbon atom, then we call them organic molecules. Organic molecules, okay? Many biologically important molecules are organic. Okay? Things like glucose, right, which is the main fuel that our body uses. We're gonna learn more about it later. Right? Proteins, these are organic molecules because they contain carbon. Okay, don't confuse the definition of organic in science compared to in food, right? If something is organic food, it just means it's grown with natural stuff, right? Okay, but in the context of what we're talking about, organic just means it contains carbon. It doesn't even have to exist within a living organism. Many products at home are organic and they are not found in living things. So polyester, right? Like your jacket is made of 70% polyester. That's an organic molecule. Okay. Methane, that's organic molecule. If you have a non-stick pan at home, cooking pan, the non-stick black surface, that's Teflon, that's an organic molecule, right? All it means is that it contains carbon atoms. Okay? So the people who came up with these rules, they say, all right, everything that has carbon is organic except for these things. Okay, so CO is carbon monoxide. Even though it has carbon, for some reason they don't want to call that organic. Okay, carbon dioxide, that's not organic. CN, that's cyanide, and that is also not organic. This is like poison, right? Some of you might know that. So if I give you a list of molecules on the test and I say, choose all the ones that are organic. So just choose everything that has carbon in it, but don't choose these ones. Okay. Now, water is important. We cannot live without water. Okay, so someone just requested to record the meeting. You don't have to record it yourself, okay? I am recording for you, and then I'll post it online for you afterwards, right? So there's no need for you to request a recording. What was I saying? Right, we cannot survive without water for more than a couple of days at best. And where will we find it? Oh, you guys still having trouble finding the hold on, let me. Sorry. Because if you still don't know, after each class, I will say the lecture archive has been updated to include the latest lecture recording. You just click on that. Okay, that was the homepage, right? Course homepage, and then you will find it. So far we have 2 recordings last week, right? Last week Tuesday and last week Thursday, right? You guys are the morning class, so watch the morning one. All right. So after today, I will post another link, and then I will tell you, right? Lecture archive has been updated. Is that okay?
Okay, thank you.
Yeah, no problem. All right, so yeah, we cannot survive without water for more than a couple of days. Okay, so water is very important, and it's important because of its properties. Okay, because of its properties. So we're gonna look at some of its property here. Water molecule is what we call a polar molecule. A polar molecule means, here, listen carefully. A polar molecule means part of it is slightly positive and part of it is slightly negative. Okay, so let me draw this out for you to explain what it means. Okay, so here we have a water molecule with an oxygen, oh my goodness, oxygen here, and then hydrogen here. Okay, so oxygen, hydrogen. They are sharing electron between the oxygen and the hydrogen. Okay, this is a covalent bond, so sharing of electron between oxygen and hydrogen atom. But it is an uneven sharing. Okay, meaning even though they're sharing, but one of the atom actually kind of hogs it a little bit. Okay, it is trying to pull the electron towards itself. So it turns out oxygen has more of an attraction for electron than hydrogen, and so it will pull the electron towards itself, right? By pulling the electron towards itself, it makes this part slightly negative, okay? And it makes the hydrogen slightly positive, okay? Overall, it's still neutral, okay? But one part is more negative, one part is more positive. So when we put another water molecule next to it, okay, you can draw a water molecule like this, kind of like an upside down Mickey Mouse. The slightly negative portion of the oxygen will attract to the slightly positive hydrogen of another. Right? So this attraction is what we call a hydrogen bond. Okay, so this is attraction between water molecules. Right? That is what allows water to kind of cling on to each other. Okay. I want you to visualize this. All right. Let's say you have a penny. Okay. I mean, we don't really have those anymore, but like a penny or a dime. Okay. And you drop water onto it, right? How many drops do you think you can fit? Like if you have like a little dropper, eyedropper, how many drops do you think you can fit? Right? Some people say a lot, some people say 3. You know, if you actually do this, you might surprise yourself. Okay, you can easily fit like 20, 30 drops on it. Okay, I'm talking about like a typical eye drop, right? With a drop of water like that, you can fit a lot on it, and you can see the water will form a dome shape, right? They don't just fall over. And the reason it's able to form a dome shape like this is because the water molecule is like hanging on to each other because of the hydrogen bond, right? It creates what we like a film, right? We call that surface tension, okay? That's why the bugs can walk on water, right? Those water striders things, right? They could dash around water because of the water tension. And that is what the hydrogen bond is doing, okay? So when we say, in case you missed my point, when we say that the water molecule is polar, right, we are saying overall is neutral, but part of it, the oxygen part, is negative, and part of it is slightly positive. Okay, and when you have water molecules next to each other, they act as magnets that would attract each other. Okay, this attraction that you see here, that is the hydrogen bond. Okay, it causes them to be clingy. Okay, that's the same reason why you can suck water up a straw, right? They pull, you suck one up, and then they just kind of pull the next one up. Okay. Water is also very useful because it is a good solvent. Okay, a good solvent is something that could dissolve substances. So if you think about like Kool-Aid, right, and water, you mix them together, then you get the drink, right? The drink here is a solution. And the Kool-Aid here is the solute, the thing that is being dissolved, and then solvent is the liquid portion. Okay, so water is a good solvent, meaning it's able to dissolve many different things. Okay, so you can dissolve sugar in it, you can dissolve salt in it, and all those electrolytes that we talk about, all those ions, they dissolve in the water component of our blood, right? Okay. So things that can dissolve in water, we call them hydrophilic. Hydrophilic. Philic means loving. Hydro is water. Okay? So these are water-loving molecules, and typically they are polar substance. So let's take salt, for example, right? NaCl. So this is what NaCl solid looks like, salt crystals. And when you put it in water, the water molecules will pull them apart, right? The chlorine is negative, right? I explained to you why it's negative earlier, right? They like to pick up an electron. So I want to ask the class, okay? We haven't done a poll for a very long time. Hopefully you are still engaged with me. A here, okay, I want to ask you, which part of the water molecule will surround the chlorine when you dissolve it? Is it the hydrogen part or is it the oxygen part? Please let me know. Okay, we have a bit of B is oxygen, yeah. A is hydrogen, yeah. So I see that we have a bit of a split in the class. That's okay. All right. So maybe I wasn't being clear, right? Okay. We have to understand opposite attracts each other. You guys understand that, right? Like positive attracts negative. We good with that, right? Okay. So here, the chlorine is negative. Then you really have to think about the water molecule, the H2O, right? The Mickey Mouse I was talking about. Right? Which part is positive? Right? Is it the hydrogen or the oxygen? Which one is positive? The hydrogen is slightly positive, right? That's right. And the oxygen is slightly negative. So when you dissolve sodium chloride in the water, the hydrogen is the part that will be kind of huddling around the chlorine because opposite charge attracts each other. Okay. And on the other side, for the sodium, which is positive, okay, the oxygen will be surrounding it. Okay. So if you are able to do that, then the substance will dissolve in the water. Okay. We call these molecules hydrophilic. Hydrophilic. So give me something else that's hydrophilic. Again, you don't have to be all like scientific about it. Just think about daily lives, right? What else can you dissolve in water? Sugar,
Salt.
yeah.
Sugar.
Sugar, good. Anything else?
Salt.
Salt, yeah. Honey, yeah.
Vinegar can't dissolve in water.
What's that? Sorry.
Can vinegar?
Vinegar can definitely dissolve in water, right? Although when we say dissolve, we usually talk about like a solid in a liquid. But you're right. But you're right. When you mix vinegar and water together, they don't separate, right? Like oil does, right? Exactly. So
how come when you put vinegar in like salad dressing, it stays on top, the oil stays on top and the other one went down?
yeah,
You have to shake it to mix it together.
oil is different, right? Oil is
Oil
not.
and vinegar, though, okay.
Yeah, that's right, exactly. Milk, yeah. So all these things that can dissolve in water, we call them hydrophilic, okay? If it mixes with water, we can say they're hydrophilic, right? And you brought up a good point, right? Not everything is hydrophilic. Something like oil, right? If you mix them together like salad dressing, right? The oil, even if you shake it, right? If you let it sit after a while, it will flow back to the top, right? So these are hydrophobic. Phobic is like to be afraid of something, to like if you are like claustrophobic, right? Like you're afraid of like tight spaces. So hydrophobic is water hating, water repelling, if you would. Okay, so these are usually non-polar molecule. All right. Now, in case you forgot, polar means it's neutral. Overall, it's neutral, but one part is slightly negative, one part is slightly positive. And that's because the electrons are not being shared evenly, right? Okay. In a non-polar molecule, there is no slightly positive or negative part. The whole thing is just, the way it is. It's neutral, okay? There's no uneven electron distribution. And these things tend to not dissolve in water. Okay, so oil is an excellent example. Anyone else have other examples that they could think of? Just like on top of their head. This one is a little bit trickier. But coffee dissolves in water though, right? Kiana? So that's hydrophilic. Anything that would like, if you put in water, it would definitely flow on the top. Cinnamon, cinnamon. I mean, like I see what you mean. If you dump a bunch of cinnamon powder, it would stay on top. But if you stir it, right, I think it dissolves in the end, right? Okay, gas. Yep. Sand. Okay, yeah. I was thinking about wax. Okay, wax is another one, right? If you drop wax in there, it's not gonna make. Okay, so that's hydrophobic. I see what you guys are doing though. Like, like you could say, oh, calculator, right? It's hydrophobic, but that's not really like it's true. You can't dissolve a calculator in water, but that's not really the proper use of the term, right? Like a lot of things like glass doesn't dissolve in water, but that's not what we are talking about in this context, right? We're talking about like something like oil, like butter, like wax. All these things don't dissolve, right? We're not necessarily talking about like a block of wood necessarily. I hope I'm making sense here. Okay. All right, we are almost done. Just a couple more slides with the chemistry, and then we will have a break. Okay. The last chemistry bit that you have to understand is this concept of pH, okay? I'm gonna keep it very simple. pH is a measurement of the concentration of hydrogen ions. How much H plus is in a solution. Okay? The higher the concentration of H plus, the lower the pH, okay? And the more acidic it is. pH goes from 1 to 14 generally. If the pH is less than 7, then we say it is acidic. So help me out, nice brainstorm. Give me something that's acidic. I'll give you an example. Orange juice, that's acidic. What else is acidic? Lemon, good. What else?
Vinegar?
Vinegar, that's right. Urine can sometimes be acidic, yeah, especially the one that you feel the burning sensation. Those are pretty acidic, but urine can also be basic.
How about
Coffee,
bleach?
yeah. What's that? Sorry.
How about bleach?
Bleach is actually basic. We the opposite of acidic. We'll get to that later. Yeah. People say grapefruit, lime, so all the citrusy stuff, right? Vinegar. Do you know you have acid in your body? Okay, like in your stomach. That's what helps you digest your food, right? Okay, so all those things are acid. They are usually sour, they are corrosive, okay, and they have a pH less than 7.
But why does the pH in the body has to be under 6? Or otherwise it's become an acid. Okay.
Yeah, that's right. So lower H plus, if you have less H plus, then it's a higher pH, then it's less acidic. When something is higher pH, sorry, when something has a pH that is higher than 7, we call them basic. Okay, so pure water is neutral, and that has a pH of 7. Okay, so things that are by the way, not everything has to be acidic or basic, right? Sometimes they don't have any pH associated with it. Okay, like salt water, it's just is also neutral, right? But you know, don't there just know that there are exceptions. It's one of the first thing I taught you, right? Not everything is so clear cut in science, right? Sometimes it doesn't have to be this or that, right? Okay, so things that are basic would include like cleaning products, right? So like baking soda, bleach, soap, right? And in fact, our blood is a little bit basic. Okay, our blood is about 7.35 on the pH scale, right? And this gives you like a bunch of examples of what the pH are. So normal blood pH, as I told you, is about 7.35 to 7.45. It's a very narrow range that is compatible with life. If you have too much acid in the blood, then the condition is called acidosis. When you have the suffix osis, it means too much of it in the blood. So acidosis is too much acid in the blood, and that happens when it's less than 7.35. Too much base is called alkalosis, okay? And that's greater than 7.45. Outside of these range, right? Outside of the 7.35 and the 7.45, it could be very dangerous for you. Yeah, you could fall into a coma, your body could shut down, kidney can get irreversibly damaged, and you know you're in great danger. So that's why your blood has a lot of ways to balance out the changes in pH. I mean, we don't slip into a coma every time we enjoy a glass of orange juice, right? Even though orange juice is very acidic, right? Because we have ways to prevent these rapid changes. Okay, so your respiratory system, your urinary system can also work together to help counteract these changes in your pH. Okay, so that you will learn like next semester. And that's it for the chemistry stuff. Okay, just very quickly, let's do one poll question, and we will have a break. All right, I will let you read it first because some of you were telling me it's blocking your the poll is blocking your screen. All right, so I'm gonna launch the poll. I hope you guys get this right, okay? Okay, I'm gonna be closing the poll soon. Anyone else wants to log in their answers? Okay, so the correct answer is uneven distribution of electron. Okay, a lot of you also chose hydrogen atom has a positive charge. It's correct to say that hydrogen atom has a positive. It's not. Sorry, it's the hydrogen atom has a slightly positive charge, but that's not the reason why it is polar, right? Ultimately, what results in the slightly positive charge and the slightly negative charge is because the electron is unevenly distributed. Okay, and everything else is it's incorrect. Okay, so why don't we take a quick 5-minute break? We'll come back at 9:42, and then we will learn the macromolecules afterwards. Okay, see you in a bit. All right, let's keep going. I was looking at the practice the quiz. Okay, like you should, before the actual quiz next Wednesday, you should try out a practice quiz because you need to install the lockdown browser, right? So let me show you where to get that. Right? View as student. Okay, so this is what you will see when you log on to the course homepage. Okay, and what you want to do is you want to go to assessment, quizzes. All right, these are all the self quiz for all the different units, right? And then you see that these are future quizzes. Your first quiz is going to be on September 21st, right? And it says it requires Respondus lockdown browser. Right? So what you want to do here is you want to click on the first one. Okay, here the current quiz here, scientific method self quiz requires Respondus lockdown browser. You click on that, and you have to download and install the latest version of lockdown browser first. Okay, and then you can launch the lockdown browser from here. You want to do that because I have some students who are emailing me and saying that they have some technical difficulties. You want to get that all sorted out before the actual quiz, right? If next Thursday is the first time you do this and you run into problem, you might not be able to fix it on the day, right? And by the time you fix it, the quiz might be over, right? So that's why I created this practice quiz for you. It doesn't count for grades, okay? Only 7 of you have done that. Right? The rest of you have not had chance to do it yet. So I encourage you to get that done today. Okay, just get it installed. You also need it for your math and chemistry class, right? For the lockdown browser. So just get it out of the way. Make sure that you know how to use it. If you have trouble finding the quiz, okay, again, it's assessment quizzes. That's all you have to do. In the end, if you can't find it, just email me. I'll show you where it is. Okay, back to our scheduled program. Now that we have a decent understanding of the chemistry behind the basic chemistry background, we're gonna talk about the macromolecules. There are 4 major macromolecules that are found in the body, 4 categories, if you would. They are listed here. The carbohydrates, which is our preferred form of energy, proteins, lipids, as well as nucleic acid. We probably don't have time for all of it today, but we will definitely, most likely, finish carbohydrates. Macromolecules, macro means really big. So these are really, really big molecules. How big? Well, if you think of water molecule, it has 3 atoms in it, right? 2 hydrogen, 1 oxygen, total of 3 atoms. That's pretty small. When we talk about the macromolecules, we are talking about thousands of atoms in some cases. So really quite big compared to something like water. And we can think of the macromolecules as polymers. Okay? Polymers are basically long chain of similar subunits that has been connected together. Okay? So we have these individual units that are called monomers, and you can link them together to form a long chain. Okay, these are called polymers. All right, so each macromolecule has its own type of polymers. Has its own type of monomers, rather. Okay, don't worry about memorizing the chart here for now. We will go into more detail of each type as we progress through the class. But right now, just understand macromolecule is this long chain of subunits, and it forms a polymer. So how do we connect the monomers together? Right? This, don't worry about what the hexagon is at the moment. It will make more sense in a bit, okay? For now, just understand the corners of the hexagon represent a carbon. Okay, so these are just carbons all around. Okay, but we don't have to draw them out. Okay, just understand that they're there. So there is an OH on one of the monomers here, and then there's an OH on the other one. When we want to connect these two things together, we can use a process called dehydration synthesis, okay, or sometimes called condensation reaction. When you dehydrate something, or when there is condensation, it means water comes out, right? So basically, you would take an H from one of the monomers, and then you would take an OH from the other one, and then you will remove them. Once you remove it, you get a water molecule, and you are able to connect these two things together, and now we have a bond. Okay, so this is two monomers connected together. You can do the opposite. You can take the polymer and you can add water to it, and then you can break it down back into its original state. And this is called hydrolysis. Lysis is to break. Hydro is water, right? So you are breaking a bond with water. Now, all that can be overwhelming, I guess. Let's write it down here. Okay, so essentially, we have these monomers. Okay, these are individual monomers. And you can connect them together. You can connect them together into a chain. Like kind of like, you know, doing a bead necklace, right? So that is that is polymer. So how do we do this? How do we link them together? We use a process called dehydration synthesis, right? Right? Or condensation reaction. Okay. So plus like some water molecule. Okay. N of them. We don't know how many. And we can break the polymer. Like when you eat proteins, when you eat like cheese, meat, that's proteins, and you want to break it down, then we have to add water molecule to it, and the process is called hydrolysis. Hydrolysis. Okay. Now listen to me carefully. If I have two monomers and I want to link them together, and I want to link them together, how many water molecule is it gonna come out? If you take a monomer, and then you remove, you link them together by hydrolysis. Sorry, by dehydration synthesis. How many water
Two?
molecule come? Sorry, how many?
4?
Let's
Or
take
maybe 2, because are we adding them? Because I would say 2.
yeah, just one and one take out, right? So let's take a look at a picture here. Oops, wrong one. Right over here, right?
Yeah.
This is one of the purple circle and then another purple circle. When you join them together, you take an H, you take an OH, you remove one water molecule. Okay, H2O. All right. So this is one H2O. All right, let's try this one. Let's say I have 5 of these balls, and then I link them together. Yes, I will upload the notes to eCentennial after class. Yeah. I also did for last week's material. Okay, I'll show you where it is afterwards. How many water molecules if I need to connect 5 monomers together here? Okay, let's do a poll. Let's see what you guys think. Okay. A is 1, B is 2, C is 3, D is 4, E is 5. Okay. How many water molecules will come out? Okay, I had 14 responses. What about the rest of you? Just choose something. Okay. Choose what you feel is right. Okay, thank you for participating. Every time we'll join 2 together, we need to have 1 water molecule, right? So look, that's 1 water molecule, 2, 3, 4. Right? 4H2. Okay. Every time you join 2 things together, you need to remove a water molecule. Okay, so that's the answer. For those of you who don't quite understand this, can you let me know what's confusing you? Ask a question, and then I can help you out. Okay. Or is it clear now? And what about like 100? 100 of them. 100 of them. How many? How many water molecules? 99. Right? That's right. It's just 1 less than the number of things you need to connect. All right. Shayna, do you have a specific question? Is that you confused? Okay, let me know if you have the specific question, okay? And then I'll address it. All right, so hopefully that makes sense. We're gonna go back to here now. So here's another poll question. Right? Take a look first. Right? Read it, and then I will relaunch the poll so it's not blocking you. Okay.
Excuse me, sir. Can you explain the question, please?
Can I explain the question?
Yes, please.
Okay, yeah, I'll go through it after we finish with the poll, okay? So this would be an example of an application question, right? All right, so we can see here, there are two monomers. One of them is a hexagon, the other is a pentagon, right? And when we want to link them together, we have to remove a hydrogen from one of them. It really doesn't matter which one you take it from. And then you have to remove OH from the other. And then you can connect it, right? So the answer should be the one that has one hexagon connected to a pentagon with an O in the middle. Right? So that would be B. That's the answer. Okay. A lot of you chose D, but D is like two hexagons here, right? We're trying to connect a hexagon with a pentagon. Does that make sense? Please let me know if you have any question. No, we are good. All right. You know what? Let's just for good measures, right? Let's just do one more, in case. All right. Like what? Because like you probably will see this question on the
Sir,
test.
oh, that's what I was just gonna ask. These
That
questions will be on the test.
yeah, some of them will. Okay, some of them.
Okay.
Okay, let's say we have a thing here. Like again, you don't have to know what the pentagon is, like what it means. Okay, like I'll tell you what it means in a bit, but right now it doesn't matter. Okay, so let's say I have this guy and this guy, right? Like, and you want to connect them together through dehydration synthesis. What's the answer going to be? While you're working on this, like, by the way, like everybody's test will be slightly different, right? We have a really big question pool. So like, you know, I don't know. I don't know if you guys talk to each other, okay? But like, don't be surprised if like, you know, your friend had a particular question and you didn't have that, okay? Because everybody is gonna have a slightly different test. All right, so hopefully, I mean, I can't see what you're writing, but hopefully you would have a pentagon and you would have a square, right? And then you would connect them with an O in the middle, right? And then don't forget to add the water because like it comes out, right? Is that okay?
Yes.
Yeah. Okay, so I'm getting a few yeses. And for the rest of you, if you still don't
Yes,
understand, that's okay. Just like, you know, ask me afterwards. It's not a problem at all. Okay, moving on. Carbohydrates. That's our first macromolecules, right? So here we go. Carbohydrates are organic molecules, right? Meaning it contains carbon, right? But it also contains hydrogen and oxygen. Nancy asked, do you have a study sheet for this? Yes, there is a study guide for every single lecture, and you will find it over here, okay? Content, lecture 2, study guide. All right, and I posted the answer for the study guide for last week already, right? I don't know if you guys had a chance to look at that. So carbohydrates has a general formula of CnH2ON. What does that mean? So let's say N is 6, right? Then it will be C6H2O6. Okay, you would have 1 part carbon and 6 part hydrate. Hydrate as in like water. So that is going to be C6H, 6 times 2 is 12, O6. Okay. So N can be any whole number. It could be 2, could be 4, could be 5, could be whatever. But all carbohydrate molecules would follow this general formula. Okay. Now, I know it's a lot of material, right? Which is why I told you it's okay to come up with a cheat sheet for your test, right? For those of you who missed the first class, you don't have to do the test with no notes, okay? You can have some help sheets in front of you to make it, you know, a little bit easier for you. Why do we need carbohydrates? Well, carbohydrates is the preferred form of energy that our body uses. It provides quick and short-term cellular energy. All right. And in some other organisms, not humans, but in some other living things, carbohydrates are important because they form structural components. So the plants, the fibers of the plants, that's actually a type of carbohydrates. The shell of a clam, of lobsters, of crabs, the shell is made up of a type of carbohydrates, okay? So for humans, we use it for energy. For some other organisms, they use it for structural support. When we have carbohydrates in the system, we break it down into glucose. Okay? Glucose is a type of simple sugar, we call it, okay? And we use glucose by burning it in the presence of oxygen. That's why we need oxygen to survive, right? When you breathe in oxygen, you actually will react it with glucose, and it will become carbon dioxide, which we exhale, as well as water. The water, you know, we either pee it out or it stays in our blood. So this process happens within our cells and it produces energy for our body. This is called cellular respiration. We will learn a lot about this process in lecture 5. Okay, but that's the main reaction that provides us with energy. Where do we get carbohydrates in our diet? There is no shortage of carbohydrates in our diet. The main, most common source of carbohydrates would be from starch. Okay? So you might get it from rice, okay, corn, wheat, potato, pasta. Some people like to have complex starch. So, you know, they say like white rice is not very good forms of starch because it's like too much carbs. So some people like to eat like grainy starch, right? Like quinoa, right? Maybe brown rice, right? Maybe some lentils, for example. Those are more complex carbohydrates. It's a healthier choice. But that's the source of carbohydrates, right? You can get it from fruits. Yeah, chia seed, exactly, right? You can get it from fruits, right? And that exists in the form of fructose, okay? Corn syrup, of course, is not very natural, but nevertheless is a source of fructose. You can get it from dairy product, right? Lactose is found in milk, ice cream, yogurt. Candy bars have a lot of sucrose. Sucrose is basically your kitchen sugar. Okay, the ones that you have in your cabinet, that's sucrose. So again, no shortage of carbohydrates. You eat any regular meal, it's likely to have some carbohydrates in it. Remember, these macromolecules are polymers. They're very long molecules that are made up of individual monomers, right? So there are 3 common monomers in carbohydrates that we will learn: glucose, fructose, and galactose. And I'm sorry, but you will have to memorize these things. Okay, I will ask you on the test, on the quiz, right? Which of the following is an example of a monomer for carbohydrates? You would have to know how to identify them, right? And like I said, if you have trouble memorizing them, you know, put them on your cheat sheet or something. So these monomers are collectively known as monosaccharides. Saccharides means sugar. Mono is single. You don't have to know how to draw them, and you don't have to know how to identify them. I'm not going to give you a picture and ask you what it is, okay? But you can see the chemical structure is a hexagon. right? That's what the hexagon was, right? In a couple of slides earlier, right? It represents something like a glucose molecule, okay? That's what it is. So glucose looks like this, fructose looks like this, and then galactose looks like this. Okay? I'm just showing you, right? So these are the monomers. Now what you can do is you can connect them together, right? Using dehydration synthesis. Right? So let's take a look. You can take a glucose and you connect it with a fructose. Now, how do you do that? I already showed you earlier, right? You have to remove a water molecule. So you take the hydrogen and you take the OH from the other and you remove the water molecule and then you form a bond, right? That's why I didn't show you the whole thing at the beginning, because like you look at this is like super confusing, right? Like what are all these things doing, right? That's why earlier here in the poll question, I only show you the hexagon and I show you the pentagon, right? So you remove the H from one and you remove the OH from the other. So that could be a glucose and that's a fructose, right? So here, when you take the glucose and the fructose and you connect them together, you remove the water molecule, you end up getting sucrose. Where do we find sucrose at your home again?
Sugar.
The kitchen, that's right, kitchen cabinet, okay? Hopefully you have some sugar at home, okay? It's kind of like essential, right? Thing to have. And then you have water afterwards, okay? So this thing that you get the sucrose, because it has two simple sugar connected together, we call it a disaccharide as opposed to a monosaccharide. Okay, so glucose plus fructose gives you sucrose. Now we can have other combinations here, guys. We can have glucose plus glucose. That gives you maltose. If you look at the back of a candy bar, you look at the ingredient of candy bar, I guarantee you that there will be maltose in there. Okay, it's just two glucose linked together. Glucose plus galactose will give you lactose. That will be in dairy stuff, right? Milk, ice cream, yogurt, cheese, right? Gelato, those things will have lactose in it. And again, the things here on the left, those are monosaccharide, single sugar. And these things that you form when you connect two of them together, disaccharide. Okay, and we already look at like glucose and fructose gives you sucrose, right? Kitchen stuff. And you'll find maltose in like, you know, corn syrup, sugar, like candy, right? A lot of stuff actually. So take a look at the ingredients sometimes, and you will find these things that you previously might not know what it means, but now you know it's two glucose together. Right? So you should know all the monosaccharides and you should know the disaccharides. But that's not a polymer, right? A polymer is many, many, many monomers connected together. These are just two, right? So we need to put more on them. But before that, there is something called lactose intolerant, right? Lactose intolerance, right? If someone is lactose intolerant, it means they don't have the proper it's called an enzyme. Okay, they don't have the proper chemical in their body to break down lactose. Okay, so when they eat anything that has lactose in it, they cannot break it down into glucose and galactose. Then the bacteria would basically feast on them. Okay, and then the bacterial activity increases and it causes like a lot of bloating, gas production, and potentially diarrhea. So people who are lactose intolerant, they can buy these things. They are basically, you can see here, right? They're called lactase enzyme. We'll learn more about enzymes later, but it's a protein basically. Okay, so your body cannot make the lactase on its own, So you take the lactase before you have your, banana split or something. You pop one of these pills and then you eat the dairy product, and then the pills will actually able to break it down for you to avoid these symptoms. Okay. So we started with monosaccharides. We can connect them together to make disaccharides. Okay? We connect them by removing a water molecule, right? And then the next step up is we add more and more and more to it, and ultimately we get polysaccharides. Polysaccharides. Okay, so these are very long, sometimes branched chains of sugars. Okay, hundreds of units long, thousands of units long. And here are some common polysaccharides. Okay, we have cellulose, glycogen, and starch. I will explain what these are in a second, but they are all just long chains of glucose, multiple glucose linked together. Okay, so cellulose is like single branch, a single strand. Glycogen is like very, very extensively branched. They are all glucose, okay? Glucose in the main branch and then more glucose coming out on the side. Starch is like a little bit branched. Okay, so it's all the difference is how the glucose are being connected together. But ultimately, they are just multiple glucose that are connected. Okay, and because of the difference in how they are linked together, it gives them different properties. So that's cellulose. We do not have cellulose in the body. Cellulose is the main component for the fibers in plants. Okay, so we haven't learned cells yet. So for those of you who don't know, cells are the basic units that makes up living organisms. And for plants, their cell, this is a cell, their cell has a wall that surrounds it. Okay, so that's what the cell wall is. We will learn more about it in lecture 3, but that is made up of cellulose. Okay? That's the fibrous part of the plant. When you eat celery stick, it's crunchy. That's the cellulose from the cell wall. Okay, the tree bark, right? We don't eat that, but that's also a form of cellulose. Even though we don't digest cellulose, it's very important to have fibers in our diet. Right? Dietary fiber is essential to help your intestinal tract to move along. If you're someone who don't eat a lot of fibers, and you want to change that, you actually have to slowly increase it. You can't just like go all out, full fiber meal, on the next day, because a sudden drastic increase in fibers will actually clog your digestive tract. It will cause bloating and a lot of gases, right? So you have to increase it slowly. Right? But dietary fiber is important for good health. Animals that feeds on grass, grazing animals, we call them, right? They have a special kind of bacteria in their stomach that helps them break down the cellulose. Okay, so cows, right? If you ever observe a cow, they actually chew a lot. Okay, how many stomach does a cow have? Anybody know? So it's a weird question to ask, but yeah, it has like more than one stomach, right? 3 stomachs, you guys are saying. Then that's because the grass is so hard to digest, right? Same thing for like other grazing animals like deers and stuff like that, right? So they have these special bacteria that helps them breaks it down, and then they actually have to kind of regurgitate, barf it back out, and then they have to chew more, and then they have to ingest it again for a second round of digestion. Okay, and that's why cows are bad for the environment. If you don't know that, every time they burp out the grass to chew it again, they burp out methane gas as well, and then the methane gas goes up to the atmosphere and it causes global warming, right? So that's why people say raising cows is actually bad for the environment. In any case, we don't have those special bacteria, and that's why we cannot digest cellulose. Okay, if we try to eat grass, it would basically clog our digestive system. We won't be able to get much nutrient from it. Okay, so another kind of polysaccharide is starch. Starch is the storage form of energy in plants. Okay, you find them usually in roots. Okay? So the potato, the yam, cassava, all these are like root of a plant, right? And they have a lot of starch in it. So plants, they store these starch for themselves to use when it's like winter, right? When there's not a lot of sunlight available, they want to use the resources. But of course, we dig them up and we eat them and we extract the energy from it. So storage form of energy in plants is called starch. We eat our food, the starch, and then we use what we need, okay? Because everyday life is energy consuming, okay? You walk around, you run around, even sit here to listen to me, right? Your brain needs to interpret what I'm saying, right? So that uses energy as well. So we burn a lot of it. Whatever we don't burn up, if we have excess, then we store them, right? So the storage form of energy in animals is what we call glycogen. Okay, we store them in the muscles, we store them in the liver. Okay, for those of you who don't know, the liver is like, this is your diaphragm, right? Okay, the muscle that helps you breathe. Okay, and then your liver is like on the right side, right beneath the diaphragm. Okay, so you store a lot of glycogen there as well. So if you skip breakfast this morning, you're like, oh no, I'm late for class. Well, actually, that it's unlikely because you could be eating and I wouldn't know it, right? But whatever. Like if you skip breakfast, okay, then you are running on your glycogen reserve. Your body will go to the liver and your muscle and break off one of these glucose, and then it will burn it up to produce energy, right? In cellular respiration. Okay. So that's the summary of all three kinds of polysaccharides. We have the starch, which is just a strand, single strand. We have the glycogen that have some branches, right? Actually, starch can branch a little bit as well. And then we have the cellulose, which is the fibers that we find in the plants. Now, there's one last one here. It's called chitin. Okay? Chitin is a polysaccharide that is not made up of glucose or fructose or galactose. It's made up of a special kind of monomers that is a glucose with some nitrogen on it. Okay, you don't have to really know the details to it, but this is really strong. Okay, that is the stuff that creates the exoskeleton, the shell of insects as well as of crustacean, right? These are like crabs, lobsters, shrimp, the hard part of it. That's made up of chitin. Okay, we don't have chitin. Humans don't have chitin, but we actually use chitin in medicine, right? Chitin, because it's a biodegradable substance, it's excellent to use it as surgical threads. Okay, so like if you remove your wisdom teeth, they can stitch you up with chitin threads, then you don't have to go back to remove the threads. It will just naturally dissolve in your mouth. Okay, same thing for like other kind of surgery, right? So that's good because it's able to degrade on its own, and it allows the wound to heal a little bit quicker that way. So that is all your polysaccharide stuff. You can do the concept check question on your own, and we'll take it up next class. And that's it for today. Now I actually, so this is the study guide, right? You should do all these questions on your own, right? For example, complete the following reaction. Something plus something is maltose, right? So you want to be able to fill that in. These are the 4 kinds of polysaccharides that we talked about, right? So you want to fill it in as well. Where can we find starch, for example? You will find it in the roots of plants, and the main function is to store energy. Okay, so don't let the material build up. Okay, you want to work on these things on a weekly basis. And so next class we will try to finish the lecture. We have 3 more macromolecules to talk about: the lipids, the proteins, and the DNA. All right. That's it. Okay, thank you. I will see you all on Thursday, 8:30. If you have questions, feel free to stay behind and ask them.
Sir,
Yes, Georgia, go ahead.
if